In this video, we're talking about the fundamental theorem of algebra. And the fundamental theorem of algebra says that if f of x is a polynomial of degree n, which is 1 or higher, then f of x has at least one complex, 0. We can extend that theorem and say that if f of x is a polynomial of degree n, which is greater than 0, so 1, 2, or 3 or higher, and a is a non-zero real number. I'm going to highlight it so we could focus on it. Then f of x has exactly n linear factors: x minus c, x minus c1, x minus c2, x minus c3, so forth, until x minus cn, multiplied by that number a. Okay, so nth degree polynomial has n factors, n linear factors, where each coefficient in each factor is 1 in front of x. And then we have a multiplier in front, a. And c1, c2, c3, c4, and so forth in this expression are complex numbers, and they are actually zeros of or roots of f of x. All right, so I hope that makes sense. If not, rewind and listen again. Okay, we're gonna I'm gonna show you what that means on practice in a little bit. But before we get there to that, I want to read this to you. It says real numbers are a subset of complex numbers, but not the other way around. What that means is that a complex number is not necessarily imaginary. So, for example, a complex number could be, well, 3 plus 7i. That's a complex number. But 3 is also a complex number. So it's not necessarily imaginary. A complex number doesn't necessarily have the imaginary portion to it. So like real numbers, like a square root of 17, it's also a complex number. But real numbers are also complex numbers. Basically, that's what we just said right here. So yeah, all numbers are considered complex numbers, but not every complex number has imaginary part to it. Okay, moving on. Example 6. We have f of x, which is 3x cubed plus 9x squared plus x plus 3, and we need to find all the zeros of this polynomial. So we're gonna write the p, the factors of the last coefficient. So we have plus or minus 1, plus or minus 3. And for q, we have same thing, plus or minus 1, plus or minus 3. So possible zeros are 1 over 1 is 1, 1 over 3, plus or minus 1/3. Also, we have 3 over 1, so plus or minus 3. And 3 over 3 is 1, which we already have. So we have 6 possible zeros. And like we said, what we're going to do, we're going to divide our polynomial by these zeros. And I mean possible zeros because, I mean, we just have to check them to see if they're really zeros. Let's, for, you know, to be spontaneous, start from the right side and try 3's and -3. Okay, so don't forget to include all of the powers of x. So we have 3 for x cubed, and then 9 for x squared, and 1 for x, and 3 for x to the 0. Okay, so divide by 3. Bring 3 down. 9 positive, that's 18 times 3, that's 54. It's not gonna do it. So 55. And then we have times 3, 150 plus 15, 165. So I can tell right now that no, it's not a 0. The function value of at x equals 3 is 168. Okay, let's try a negative 3. Same thing. Bringing 3 down, negative 9, 0. I like it better. 0, 1. Look at that. 1 times negative 3 is negative 3, and we are getting a 0 as a remainder. And that means that, let's write it down. That means that x equals negative 3 is a root of this polynomial, or a 0, is a 0 of f of x. And what that also means, and x plus 3 is a factor. Okay, so let's write it. Let's write the factored form here. So the factored form is x plus 3. And then here, to find this trinomial here, we're going to insert powers of x. So 3 is 4x squared, exponent of x squared. 0 is exponent for x, and 1 is a freestanding term. So we have 3x squared there, 3x squared. And we also have just plus 1, because the coefficient for x term is 0. Okay, so what's next? Next, we're gonna try and find, zeros from this portion. Okay, so I'm gonna actually continue here. We're gonna write 3x squared plus 1 equals 0 and solve this. So 3x squared equals negative 1, and then divide both sides by 3, negative 1/3, and then unsquare. So x is gonna be positive or negative square root of 1/3, which is positive or negative root of, actually it's negative inside, negative 1 over root of 3. Okay, so I'm gonna continue here. Square root of negative 1 is I, so we have positive negative I over root of 3. And again, we need to rationalize our denominator. So I'm gonna multiply the top and the bottom by the root of 3. So we have I root of 3 over 3. And again, I like to put I in front of the radical sign so that it didn't look like it's under the radical sign. Okay, so here we have 2 more roots, okay? And like we discussed before, it's actually plus or minus, I forgot. So it actually is 2 in 1. So the first root was x equals -3. That was x1. x2 is positive I root of 3 over 3. And x3 is negative I root of 3 over 3. And these are conjugates of each other. So the we're going to talk about complex conjugates a little later. So, but just we have 2 roots. Now, if I wanted to use this theorem and say if I have all the zeros, C1, C2, C3, so forth, we have 3, then I could write my polynomial in this form. So it's some coefficient a multiplied by x minus root 1, x minus root 2, and x minus root 3. What would it look like? And okay, so I'm gonna write it here. So it looks like this. First of all, a is 3. That's our first like leading coefficient. Okay, and then we have x plus 3, and then we have x minus I square root of 3 over 3. Sorry. And we also have x plus I root of 3 over 3. So that's minus a -1. That's it. This is what it would look like. Now, if we were to multiply them back and factor 3 in, you would get 3x squared plus 1. And like then when you multiply that by x plus 3, you'll get your polynomial back. Just do it for fun. Check if this whole thing multiplies back to 3x cubed plus 9x squared plus 3 plus x plus 3. And this is how the graph of that function looks like. It crosses, it has one real 0, so it crosses the x-axis there at -3. And it has 2 imaginary, so it doesn't cross the x-axis anymore. So just that once. And I want you to try this problem by yourself. Which says find the zeros of f of x equals 2x cubed plus 5x squared minus 11x plus 4. And let me know if you have any trouble with this problem.